All right, hello everyone. So today we're working on a Calculus 1 problem. We're working on volumes today, and we have as follows. Set up an integral that computes the volume of the solid that results from taking the region bounded by the following curves rotated around an axis. All right, so it's two problems. Part A here says let y equal x plus 5, the x-axis x equals 5 and x equals 10. So all of what I just read there, that's going to form a region. And you're going to rotate that is rotated around the x-axis. Okay, so we're going to go ahead and let's take a look at what we're given. And let's see if we can make a drawing here. So we've got the graph of x plus 5, and here's the thing. You can do like a little rough sketch here. It doesn't have to be exact. It'll be a straight line. The x-axis is down here. X equals 5 and x equals 10. So those would be like two vertical lines. Okay, so this is the region that we're gonna work with right here that's bounded by all these curves. And we're gonna take that and we're gonna rotate that around the x-axis, okay? So we make this little curve there with a little arrow saying that's what you're gonna rotate it around. So what happens is that you take this two-dimensional region and you're going to rotate it around, and when you do that you're going to get something that's in 3 dimensions essentially. And kind of roughly it would look, so when I do the rotation of the 2D region, it's like you're reflecting it around the axis, and you take those curves and it would look something like this. In 3 dimensions is what it looks like. And think of this as the picture that I had drawn earlier. Just kind of all this stuff here. And imagine, you're looking at it like I am looking at it actually right now. It's sitting on a table, and then it's going to come out. When you do the rotation around the axis, it would come around to your point of view, and it's coming out like in 3 dimensions, and it rotates around, and you would get this shape. Okay, so I once had someone say it. Another way to explain this is like you have looks like a rotisserie chicken. If you ever go to like a supermarket where they have those machines that do rotisserie chickens and they're rotating around, it's kind of like the idea in a way. You take a piece of the chicken. If you were to cut it and then if you were to rotate it, you get kind of like the whole chicken in a way. It's like what some people see it as. So I found that interesting, and that helps you out. And in our case, that figure that I have in black, you see here, let me circle it. That is the 3-dimensional shape we're looking at. Okay, so it's always nice if you can imagine, what's going on. It really helps out for sure. But if you're having trouble, you can get away with not knowing what the shape looks like. Well, anyways, the big point here in terms of our setup is when you do this rotation, you have a solid shape in here that has no gaps in the middle or anything of the sort. Okay. When that happens, that's what we're going to use what we call the disk method. There's no gaps, and when you compute the volume, it's equal to pi times the integral that goes from a to b radius squared dx. Okay, so the radius is standing for the distance from the function to the axis of rotation. That's what that stands for. And I underlined dx there because this could be in terms of dx or dy. It's going to be dx if you're rotating around the x-axis or anything parallel to the x-axis. And technically it's dy if we are rotating around the y-axis or it's parallel to the y-axis, okay? So in our case, if we were to do the computation here, how would that look like? Well, going what I wrote in blue there, this would be the volume equals pi times some integral. Now, what do I mean by the radius squared? So the radius is the distance from the axis of rotation, which is the x-axis, to the function that we're rotating essentially here. So in this case, it's this much, okay? taking that whole region and you're rotating it. And that distance is basically just x plus 5. So that is what would go in here. And this would be dx because we're rotating around the x-axis. And what are my limits of integration here? Well, the limits of integration are from 5 to 10. They're x values. So it's from where you start to where you're finishing. So 5 to 10. And that would be it right there. All right, so for our next problem, we're going to work with the same idea. Part B, let y equals square root of x, the y-axis in y equals 9 is rotated around y equals 9. Okay, so what would that look like? So we're going to draw that region. All right, the most important thing here in terms of like the pictures are that you get the 2D picture. So you get square root of x looks something like this. Y equals 9 is a straight line. And then you have the y-axis here. So this is the region we're looking at. And we're going to go ahead and rotate that along the line y equals 9. Okay. So when you do this rotation, you get a region that looks something along the lines of something like this. Almost looks like a kind of like a horn or something. And I do apologize with my drawings here. I wish I could be much better at sketching stuff in 3D, but I'm pretty awful. And the good news is that you really don't need to know how to really do a great sketch in 3D. It's just a matter of like knowing how to basically look at something and kind of get it if you can. So that's what it would sort of look like. And again, there's no holes or gaps here when I did my rotation. And my volume here, accordingly, with that formula that I use would be pi, the integral that goes from some place to some place, radius squared. Now, what's my radius, though? So my radius is this distance that I drew in blue, okay? That is the distance that I am rotating. That represents like the radius of these discs that we're using here, that we're rotating. So how would I find an expression for that? Well, the expression for that would be 9 minus root x. Why? Because this distance right here is 9, and this distance in orange is from the x-axis to square root of x is square root of x. So the stuff that you see in blue over here, that's equal to 9 minus root x. It's the difference between those two distances. Okay, so that is my radius. And then you're going to go from where to where is your next question. And it's going to go from 0, that's where we start, and all the way here where 9 and the square root of x meet each other. And that would be at 81, okay? And I'll let you work on that. Yeah, the biggest issue with these problems is really just your setup. It's always the difficulty is always what you're integrating. The integral itself is not too bad. At most you typically would do like a U substitution with these. And this one you'd have to FOIL things out and then integrate each term and so forth. But yeah, the most difficult part is always the setup. And that's the big question when you're rotating a region around an axis and you're asking to find the volume. It's either going to be, it's going to have a hole, a gap, and if it has, or not, it doesn't have a gap. That's what all of these these questions were about today, is you're going to be using a disc. However, if you do not have, if you have a hole in the middle, that's what we call a washer. And just to give you a little preview of that, we'll make another video about a washer. A washer is when you have a gap, and usually you're going to involve two functions. So let's say this is f of x, and let's say this is g of x right here. And I'm going to say, you know what? I want you to take this region that's bounded between these two graphs and maybe a couple x values or whatnot, I'm not sure. But I'm going to ask you to rotate this around, let's say, an x-axis or y-axis, whatever. And you would, when you do this rotation, you would have something, sorry, that's not a really good drawing, but you would have something that has a big gap here in the middle. That's what I was referring to, a hole. And the three-dimensional picture would look, I mean, there's a solid part, but there's a big gap here in the middle. And it's like some, yeah, not the best, but it's, think of it like a vase that's got, like, it's solid on the outside, but it's got a big hole in the middle here. Well, anyways, that's what we mean by having a hole, something that's not solid, okay, and that's what we call a washer. And we'll go over that in another video. All right, well, I thank you for your time. Hope this helps.